Okay, in lesson 10.2, we're going to take a look at developing our formulas for a circle and a regular polygon. And again, for the most part, we're going to be looking at area, but we're also going to talk about some circumference and some perimeter. All of us know what a circle is, but we may not know the formal definition. The formal definition says that a circle is a locus of points in a plane that are a fixed distance from a point called the center of the circle. What they're talking about here, this being my locus of points, equal distant to the center. Down below it says the irrational number pi is defined as the ratio of the circumference to the diameter. So pi is defined as c divided by d. Thus, when you solve for c, we are going to find that c equals pi d. Circumference equals pi times diameter. Now we also know that 2 radii are equal to diameter, so you may see that formula written as circumference equals 2 pi r. Down below it says you can use the circumference of a circle to find its area. When you think about finding the area of a circle, we're going to think about slicing it up kind of into pieces of pie. And when you slice up those pieces, we're going to fit them together every other way so that they fit together nicely. And you see we kind of start to form a parallelogram. Well, it just so happens that one side of that parallelogram, or what we're going to call the base, would be equal to half of the circumference, pi r. And the height of that parallelogram would be equal to the radius. So when we put that together, base times height, pi r times r, we find out that the area is equal to pi r squared. Now, down below it says the more pieces you divide the circle into, the more accurate your estimate will be. And I have some videos linked on my webpage that kind of shows that demonstration. So let's summarize what we talked about. If we have a circle with a diameter d and a radius r, the circumference would be equal to pi d, pi times diameter, or we said we could think about that as 2 pi r. And our area equal to pi r squared. Sometimes kids get these two formulas mixed up. They aren't sure which one is which. I always remember the area as pi r squared because we know that we label an answer for an area question as units squared. So that's how that helps me to remember. So let's take a look at some questions. Taking a look at example A, they're asking us to find the area of each circle in terms of pi and as a decimal. Now we talked about this at the beginning of the year, writing your answer in terms of pi, and the fact that an answer given in terms of pi is considered an exact answer. When we give our answer as a decimal, we're actually giving a rounded or an estimate. So here, given my circle, W, I can see that this is showing me a diameter of 18, which is going to tell me a radius of 9, right? My radius is equal to 9. So when I take a look at area being pi r squared, we know that our radius is 9. We're going to want to simplify that, but to leave my answer in terms of pi means I'm only going to take my radius and square it. I'm not going to multiply it by pi. So as an exact answer, we're going to say that this is 81 pi square centimeters. That's my answer in terms of pi. As I find that answer as a decimal, I'm going to go ahead and multiply it out on my calculator. Now I do want you to use your pi button. Using the pi button is going to be a little bit more accurate than just using 3.14 because we have more decimal places. So I can do 9 squared times pi, or I can do 81 pi. I'm going to just have you round these answers to the nearest let's see, to the nearest 10th would be fine. So it looks like we are going to get about 254.5. Now you'll notice here, the top one was an exact answer, so I said area equals. The second one is an estimate. My area is approximately 254.5 square centimeters. The second circle, we're going to approach this similar, but you'll notice my radius is 3x. 3x inches. So when I take and I have my area pi r squared, well, this one can be tricky because a lot of times kids will just say 3x squared. But this is the quantity 3x squared, meaning 3x times 3x. So as an exact answer, we're actually going to get 9x squared pi square inches. When I find that as a decimal, I'm just going to go ahead and take the 9 and multiply it by pi. So if I take 9 multiplied by pi and I round it to the 10th, I'm going to get about 28.3, but I still have my x squared. So 28.3 x squared inches squared. Question 2, it asks me to find the radius of circle J if the circumference is 6x plus 14 pi meters. Our attention to detail is important here. We want to make sure that we have our accurate information. This is my circumference. I'm looking for the radius. Well, I know that one thing, the circumference, we can think of as 2 pi r. Let's just go ahead and substitute in what we know. The circumference would be given as 65x plus 14 pi meters equal to 2 pi r. This is set up pretty easily so that I could go ahead and solve for r, right? If I wanted to solve for r, I want to get r by itself. These are being multiplied, so I'm just going to go ahead and divide by 2 pi. I'm going to go ahead and take this and divide by 2 pi. Well, what happens here? Actually, my pi's are going to go ahead and cancel out, and I'm just going to think about taking the 65x plus 14 and dividing by 2. So what I would be left with here, I have 32.5x plus 7 meters would equal my radius. Question 3 asks me to find the circumference of circle M if the area is 25x squared pi feet squared. Well, on these questions, sometimes kids can struggle a little bit finding the circumference, but they give me the area. If they give me the area, that actually is going to allow me to do what? It's going to allow me to find the radius. I know that my area is pi r squared, so let's go ahead and substitute. We have that area, 25x squared pi. That must be equal to pi r squared. Well, again, if I'm wanting to figure out my radius, because this is given in terms of pi, it's actually pretty nice. We could start by dividing. What I'm left with is that 25x squared is equal to r squared. Well, we know that if we want to solve for r, we need to go ahead and take the square root of both sides. In other words, 5x is equal to r. So my radius is 5x. Now, my circumference, 2 pi r. Well, we just found our radius, and our radius, we said, was 5x. So we just want to think about simplifying. I always want your answers given in the simplest form. Now, if I needed to give this answer in terms of pi, well, then I would say 10x pi feet. Circumference is a linear measure. If I needed this as an estimate or as a decimal, I would go ahead and take 10 times pi, rounded to the nearest tenth. Well, I know that's going to be 31.4x feet. tell you which way to state your answer. You can give it one way or the other. Doesn't matter, but you don't need to do both. Okay, now we're going to switch gears a little bit, and we're going to take a look at finding the area of a regular polygon. Finding the area of a regular polygon. What does that mean if a polygon is regular? Yeah, it's equilateral and equiangular. So as I look here, I have my pentagon, and we're going to actually need to use a little strategy to find the area. Now, you can think about dividing this up into different shapes. They're going to show us as regular, equilateral. Taking our polygon, we could go ahead from the center point and split it up into triangles. Now, when I split those up and I look at the distance from C to H or C to D or C to E, all of those segments are going to be equal in length. Similar to a radius, right? But not equal to. Now, it doesn't necessarily mean that these segments are equal to the side lengths. In this case, they are not going to be. But I do want to show you a little bit. They're going to call this right here. If I had an angle like this, they're going to call that the central angle. What would we know about our central angle? Well, do you see that all of these triangles are actually isosceles? And not only are they isosceles, they're congruent by side, side, side. And so my central angle here, if I look, I have 5 of them that would all be congruent. What else? Well, if I look at my triangle, I've added in this dotted line here. It's kind of the height of my triangle. Well, the segment that meets the side of your polygon at 90 degrees is actually called the apothem. I kind of think of that as the height of my triangle. So if I needed to do a little bit of figuring, if I wanted to know what that central angle would measure, again, I have 5 of them that would all be the same. Well, what do we know about calculating that? Well, this central angle, we could go ahead and take 360 and divide by 5, right? Because I have a full rotation going all the way around. If I take 360 and divide by 5, we'd actually find that it's a 72-degree angle. Now, when I take my triangle and I add in my apothem, I actually take that central angle and I split it in half. And so if it was a 72-degree angle to start with, now this section is half of that. So that would become a 36-degree angle. What we're going to talk about today is the fact that we could find the area of one of these triangles, which would allow us to state the area of the entire polygon. If I found the area of one of these triangles, I could simply times it by 5 and I would know my area. Now, I don't quite have enough information to solve this. I would need at least one side measure to help me out to do some calculating. We're going to take a look at that on the other side. So let's go ahead and flip our paper over. I would like to think about the area of our polygon as finding the area of one triangle and then multiplying it by the number of total triangles. Okay, we're going to come back to that above, but if we take a look at example B, and we wanted to find our area, if I wanted to split this into my triangles, well, this time I can see I have a hexagon, so I actually have 6 triangles. my very first step is going to think about finding the measure of my central angle. So here, this central angle, well, this time when I find that, I'm going to take 360, but I'm actually going to divide by 6 because there are 6 central angles to complete this rotation. And when we take 360 divided by 6, we find out that that's a 60-degree angle. Now, all of these triangles are isosceles, and if I have this side measure as 10, this side is also going to have a measure of 10. When I go ahead and think about dropping in my altitude here, my 60-degree angle, I've now split it, and so I have 30 degrees. Well, what happens is we actually have, if this is 30 and this is 90, this is going to have to be 60. What do I see about the larger triangle? Well, if this is 60, 60, and 60, right, these are actually for a hexagon. They're going to be equilateral triangles. Now, in order to help me out, if they're equilateral, this is 10, this is 10, then this bottom segment would also have a measure of 10. But when I drop in my altitude, I actually split it so that this segment here would be 5. The reason I'm wanting to take a look at that is because we need to figure out what our apothem is, or what the height of that triangle is. Now, I actually have a couple options here. I could use my knowledge about a 30, 60, 90 triangle, or I could use my trigonometry. If I use my knowledge about a 30, 60, 90 triangle, if my short leg is 5, my apothem would have to be 5 root 3. If I wanted to use my trig, well, I could maybe think about using my 60-degree angle, and we could do opposite and adjacent. So I could maybe say the tangent of 60 degrees would be opposite over adjacent, and we could solve it that way as well. In the end, either way that I do that, I should get the same answer. And when I calculate 5 root 3, I find out that this is about 8.66. If I take the tangent of 60 and I multiply by 5, this also comes out as about 8.66. Okay, so what are we trying to find? Well, let's go ahead and find the area of one of those triangles. If I have the area of my triangle 1/2 times the base, well, I'm going to do the equilateral triangle. So I'm going to use a base of 10. And my height, well, I could use a height of my apothem 8.66, or I could use the 5 root 3. Now that would give me the area of one triangle. But would you agree if I want the area of the entire polygon, I would simply multiply that by 6, my number of triangles that there are. Finding my final result, I'm going to multiply all of this together. I simply have 4 terms that I am multiplying. You just have to be careful that when you enter this, if you are going to enter the 5 root 3, you must make sure to close off that parenthesis so that you can get the accurate answer. In the end, we're going to find out that that's about 259.8. What does that mean? Well, the area of my hexagon is about 259.8 square inches. Let's take a look at one more. Okay, in figure number 2, our first object is to kind of divide it up, but also to think about what kind of shape we have. here, 1, 2, 3, 4, 5, 6, 7, I actually have a heptagon. And we're always going to think about finding our central angle. Okay, so here my central angle, I'm actually going to take 360, but now I'm going to divide by 7. Now in this case, I think that we're going to have to maybe round that central angle off. And so we're going to say that central angle is about 51.4 degrees. Now if I take a look, I'm going to kind of calculate here for this triangle. When I drop in this apothem, and I end up splitting that, if my central angle was 51.4, when I divide that by 2, that's actually going to give me that angle of 25.7 degrees right there. The reason that I want to use that is I actually need this right triangle to calculate my apothem. And when I take a look here, if this was a side length of 3, now these triangles are not going to be equilateral, they're simply going to be isosceles. So this side isn't necessarily 3, but I do know that this side is 1.5. How is that going to help me? Well, taking a look to solve for A, my apothem, I can use my trigonometry. I have a right triangle here, I can use SOHCAHTOA. I have the adjacent side, and I have my hypotenuse. Oh, no, I don't. I have my adjacent side, and I have my opposite side. So I'm going to take the tangent of 25.7 degrees and my opposite over adjacent. I'm going to take 1.5 and divide by tangent to 25.7. We're actually going to find that that apothem is approximately 3.1. So, how does that help me? Well, let's find the area of my figure. My red triangle, if I think about the area of my red triangle, well, my red triangle has a base of 3 and a height of 3.1. The whole polygon has 7 of those triangles. And then I just need to multiply together. I'm going to take 1/2 times 3 times 3.1 times 7. And we're going to find that our area is approximately 32.6 square centimeters. Okay, so a lot of work that kind of goes into that, but you're really just using your trig and finding the area of a triangle. Now at the top, I'm going to tell you that in our book, they would give us a formula for the area of a regular polygon, and it would look something like this. Area equals 1/2 times A times S times N. What does that mean? Well, A would be the apothem, and S would be the side length, N would be the number of sides. Okay, so this would be the side length, and this would be the number of sides. Well, this really is finding the area of one of the triangles and timesing by the number of triangles. And so I like to think about it just in general of splitting it up in this way. If you think about the 1/2 times ASN, the side length times the number of sides is really the perimeter. So another way they may have it written is that it's 1/2 A capital P, the apothem times the perimeter. Again, when I refer to it, I'm going to refer to it as the area of the triangle times the number of triangles. Or I may reference every once in a while the 1/2 ASN. If you have further questions on this, please stop in and see me.